Good afternoon. You're welcome to the IEAGHG webinar. My name is Abdul Aziz, and I'm a technology analyst at the IEAGHG. We are meeting virtually this afternoon to discuss the findings of the study on achieving deep decarbonization in worldwide fertilizer production. This study was undertaken by Wood and their technical partner, Ergo. So I'm going to take a couple of minutes to say a word or two about IEAGHG. IEAGHG is a technology collaboration program and are part of the International Energy Agency's Energy Technology Network. The IEAGHG is organized under the auspices of the International Energy Agency, but is functionally and legally autonomous. Views, findings, and publications of the IEAGHG do not necessarily represent the views or policies of the IEA Secretariat or its individual member countries. So who are we? IEAGHG is a collaborative international program founded in 1991 and is a member-based organization with strong membership involvement. The IEAGHG membership currently stands at about 35 members, which meet twice a year to inform and decide on technical studies undertaken by the program. The technical reports produced are used by policymakers, but are not policy prescriptive. So what we do, although our mandate covers all greenhouse gas mitigation options, our current focus is on CCS technologies with a watching brief on alternative options. Through our technical network meetings and conferences, we facilitate the dissemination of latest research and results in CCS technologies and encourage collaboration between groups. Our research is published through technical reports and reviews, and these are available free of charge to anyone within a member country or organization and can be found on the IEAGHG website. It is also worth mentioning that through our involvement with groups such as CSLF, UNFCCC, and many more, and also attendance at the COP conferences, our technical reports are provided to the policymakers to assist them in making informed decisions. The primary activities of IEAGHG include funding research into development and deployment of CCUS technologies. To date, IEAGHG has published well over 350 reports on all aspects of CCUS. IEAGHG is also actively involved in the international expert networks. The flagship IEAGHG conference is the Greenhouse Gas Technology Conference. The GHGT conference series is established as the principal international conference on greenhouse gas mitigation technologies on carbon capture, utilization, and storage. Another prime event that the IEAGHG organizes is the International CCS Summer Schools. The IEAGHG Summer School now has over 500 alumni representing over 50 countries, with many more moving to successful careers within the CCS industry and academia. I am an alumnus myself, having had the privilege to attend the 2019 summer school in Canada. The GHGT conference, which has been running for more than 30 years, is returning for an in-person attendance in October this year and will be hosted by Club CO2 in Lyon, France. For more information, visit the IEAGHG website. This is a snapshot of the IEAGHG's membership. We thank our members for their valued support. I will be moderating this webinar, and the principal researchers of the study on decarbonization of the fertilizer production are on board to present and discuss the findings of this study. They are Giorgio Collodi and Nicolas Mazzarotti from Wood, Fabiana Coselli, and Andrea Fontanella from Ergo. There is a question box, a dashboard to the right of the webinar platform. I will encourage you all to post your questions, and we will endeavor to answer as many questions as possible. It is my pleasure at this juncture to invite the senior process consultant from Wood, who is Giorgio Collodi, to start his presentation. So for the meantime, sit back and enjoy the decarbonization in fertilizer production webinar. Giorgio, the floor is yours.
Thank you very much, Abdulaziz. Please let me know if you can see the presentation. I can put it in show slideshow mode. Can you see? Not yet?
Not yet.
Is it coming?
Yes, we can see a presentation.
Okay, good.
Yeah,
Thank you very much.
We can see the notes on the right side. I think
okay. So
you need to kindly get rid of that, please.
Yeah, now should be better, isn't it?
Yes, please.
Okay. So thank you again for your presentation, Abdulaziz. So I'm Guido Collodi, and I'm senior process consultant in Wood Italiana, located in Milan office. The objective of this webinar is to present the findings of a life cycle environmental footprint of nitrogen fertilizer production with or without CO2 capture. We have considered as a fertilizer route the from ammonia to urea to UAN via nitric acid. The ammonia today is produced totally, most of the ammonia is produced primarily via steam reformer or of natural gas. In this study, we have considered ammonia produced totally or partially via steam reforming. We will see a few examples on that. And we have considered in our study 4 different regions in the world: the United Kingdom, Norway, Saudi Arabia, and the United States. We have considered 3 options in our study. The first one is the so-called gray ammonia production. That means ammonia produced via natural gas steam reforming without any carbon capture. Blue ammonia, that is again produced from natural gas, but with carbon capture from the flue gases of the steam reformer. And the hybrid ammonia production, where the hydrogen is produced partially by electrolysis, and this includes also the carbon capture from flue gases. The basis of design, the main basis of design of the study are here summarized. The natural gas is the typical one used in IEAGHG studies. So you can see is a natural gas rich in methane, ethane, with very few ppm of sulfur in it, available at high pressure. And on the table on the right, I presented the ambient conditions and the cooling system temperature for the 4 different locations. As you can see, the average temperature is as low as 5 degrees in Norway and goes up to an average value of 27 degrees C in the Middle East. There is a slight difference in relative humidity, and the primary cooling system reflects the air temperature, and is lowest in Norway and highest in the Middle East. The first case that we've studied is the base case, so-called base case, that consists of 2,000 metric tons per day of ammonia from natural gas. This is coupled, the ammonia production is coupled with urea production. The resulting urea production is 3,348 metric tons per day, and it is determined by the CO2 capture from syngas. That means that the urea produced depends on the amount of CO2 that we have available from the syngas. With this lean gas, mean natural gas, as shown before, that means rich in high in methane, there is an excess of ammonia. This excess of ammonia that cannot be converted into urea is used to produce nitric acid, ammonium nitrate, at the end the urea ammonium nitrate, and it ends up in a production of about 500 tons per day. In the next slide, I will show a simple block flow diagram depicting what I just explained. You can see on the left side there is the ammonia production. This is I recall it's a gray ammonia production. That means that all the CO2 that is produced in the steam reforming and removed is then is emitted to the atmosphere with this amount of tons per day. The CO2 that has been sorry, this is the CO2 emitted from the flue gases of the steam reformer, while the CO2 that has been removed from the syngas, it is entirely used for the urea production. This results, the result of this is that out of 2,000 metric tons per day of ammonia produced, only bit less than 1,900 can be converted into urea. The remaining part of ammonia is used to produce nitric acid, and from there it is ammonium nitrate solution, and at the end is mixed with urea and to produce some urea ammonium nitrate. This is the basic. You can see that in this case we will need basically we will need the natural gas, and we will also need some power, about 34 megawatts. The second case is we have maintained it is the case where where the CO2 from flue gases of the steam reformer is also captured. For easy of comparison of the cases, we have maintained the same product mix as the base case. That means the same amount of ammonia, urea, and UAN that we have produced. The only difference with the previous case is that we perform a CO2 capture and sequestration from the flue gas of the steam reformer. And we can see in this next slide how it appears. So this is the previous case that after CO2 sequestration becomes the following. So there is no major change compared to the previous case, other than that in this case the 90% of CO2 has been captured and sequestered from the flue gases, and due to the addition of this unit of CCS, we need more power to drive the machines included in this CCS plant. The third case that we study has been called hybrid case. Again, for ease of comparison, we have maintained the same mix of products in terms of ammonia, urea, and UAN. The CO2 is captured, as in previous case, from the SMR flue gases, and in this case is completely used as an additional feedstock in the urea plant, in addition to the CO2 from syngas. What we did compared to the previous case, that we have considered that a portion of the hydrogen is produced via electrolysis. This comes out about 30% of the hydrogen that is needed for the ammonia synthesis will be produced by water electrolysis, while the remaining 70% of hydrogen is produced with the traditional steam reformer plant that, of course, will be smaller in his front end, so that is the syngas preparation. So we try to maintain the same mix of products, and we can, I'll show you the block flow diagram in this case. This is the previous case, so without non-hybrid, and this becomes as follows. That means that some of the hydrogen is produced via water electrolysis. That means that a smaller amount of hydrogen is produced via steam reforming. But in this case, not only the CO2 captured from the syngas, but also the CO2 captured from the flue gas will be used in order to obtain the same amount of urea. So it is balanced in a way that the final mix of products is similar to the previous ones. In this case, you may see that there is a huge increase in the power demand, and this is, of course, mostly due to the introduction of the electrolysis that account for about 80% of the total megawatts requirement. So this is an explanation of the three cases we did. When we now compare the performance of the three cases, we have some elements that are, we say, location independent. So elements that are not depending on the geographical location where the plant, the complex is built. And this is the direct CO2 emission. Of course, in the base case, there is no CO2 capture from flue gases. In the CCS case, in the hybrid case, there is the 90% more or less of carbon capture from flue gases. The hybrid case has a lower CO2 emission because the steam reformer plant is smaller, as we said before. The natural gas consumption for the three cases, the base case and the CCS case shows the same identical natural gas consumption. Natural gas consumption means the sum of the feed and the fuel required by the complex. While in the hybrid case, the steam reformer plant is only about 70% of the base case, and therefore the natural gas consumption is lower. The freshwater consumption is here depicted. Compared to the base case, the carbon capture case shows a slightly minor freshwater makeup consumption because in the CCS there will be some water that is recovered from the flue gases itself. So it is accounted and recirculated to the process. In the hybrid case, of course, the fresh water is also the feedstock to the electrolysis plant. In the next slide, instead, there are the performance comparison that are dependent from the location, even if they are not so dramatically depending on the location, but still they are. For example, if we talk about the electrical power consumption, you may see that in the base case, the CCS case shows a slightly higher power consumption than base case because there is the CO capture and compression. In the hybrid case, of course, as we said before, is much higher. The differences among the geographical location are mostly due to the different air temperatures and sea temperatures. All the sea or lake temperature, because all the three out of 4 geographical locations are on the sea, near the sea, while one is considered near a lake. So this air difference determines a slight difference in power. Again, you may see that in the Middle East, the air temperature determines a slightly higher consumption of power. And in the next and final slide of my initial presentation, there is the performance comparison for what concerns the sea/lake water usage, and this is again slightly dependent on the local temperature, both of air and of water, and this is due because the sea lake water consumption is higher in warmer climates, because the amount of steam expanded, of course, to obtain the same power output is higher because the steam is expanded to higher pressure. So this determines again a slightly higher consumption of water of Middle East compared to colder regions. Okay, this ends my part of presentation of the study case, and I'll now the floor to Fabiana, who will go through the life cycle assessment.
Yes,
Please,
thanks,
Fabiana.
Guido. Thanks, Guido.
Okay.
Can you
Okay,
move
I
to
will.
the next slide?
Yeah.
Okay.
Okay.
Okay. So in this section, we present the results of the life cycle assessment study. So the life cycle assessment, or LCA, is an ISO standardized methodology for assessing the potential environmental impact and resource use throughout a product life cycle, from raw material acquisition to waste management. LCA, as you can see on the figure on the right, is based on 4 main phases. In the goal and scope phase, the aims of the study, system boundary, and functional unit are defined. The life cycle inventory phase involves the collection of the input and the output data of the studied system. In the life cycle impact assessment phase, the inventory results are associated to environmental impact categories. And finally, in the life cycle interpretation phase, the results are interpreted in accordance to the stated goal and scope.
Move to
okay. Yes. So by the LCA, it's possible to convert materials, consumed energy, and emissions into understandable impact indicators, which represents the impact on the different environmental compartment related to effect on human health, such as tropospheric ozone or ionizing radiation, ecosystems such as global warming or eutrophication, and resource depletion, such as water or fossil depletion. Next slide, please. Okay. So the goal of this study was to evaluate the environmental impact of urea and urea ammonium nitrate solution fertilizers, comparing 3 different technologies explained before, and demonstrating how deep the carbonization of these 2 fertilizers can be achieved. So 4 different regions that are representative of certain regional conditions were considered. Europe, and in particular United Kingdom and Norway, United States, and Saudi Arabia. So the focus of the study was the ammonia synthesis process, precursor of urea and UAN fertilizer. So as already before, the case 1 represents the conventional ammonia production, and it is used as a benchmark case. So in this first case, natural gas is used as a feedstock for ammonia production, and CO2 emissions are released into the atmosphere. So in the second case, we have investigated ammonia production with CO2 emissions capture, and in the third case, an hybrid production of ammonia from water electrolysis and natural gas with CO2 capture from flue gases was investigated. The functional units of the study were 1 ton of urea and urea ammonium nitrate produced in these 4 different locations. The environmental impact assessment was modeled by means of CIMA-PRO software using the ILCD method developed by European Commission. Guido, can you push the button, please? Okay. Tables, as you can see, tables on the right gives you an overview of the 16 environmental impact indicators, such as climate change, acidification, water depletion, and so on. The picture shows the system boundaries of the analyzed system. System boundaries are cradle to gate, so from resource extraction, such as natural gas, to the until the production of both fertilizers. We have not considered the use phase and the disposal phase of fertilizers, since they are out of the scope of this study. Okay, next slide. Okay. So here summarize the main assumption of the LCA study. The process schemes selected for this study are generic, location analyzed. The only exception is the presence of a seawater desalinization plant for the Middle East case. Natural gas is country specific, but doesn't match the fixed composition defined by IEA standards. CO2 consumption during the production of urea and UAN was not considered. In fact, CO2 is produced as a byproduct during ammonia production and is consequently used as input for the synthesis of urea. This CO2 is released after application in the field, so it needs to be considered in the inventory for the agricultural production. So about the data quality, all process data are based on the engineer estimates. No reference here has been defined, and some processes have been made country specific, considering electricity mixes as supplied from national grid, natural gas from national distribution network, and water supply. So in general, the environmental impact of fertilizer production investigated are mainly affected by electricity consumption. So in the following slide, the direct comparison among 4 investigated locations where fertilizer are produced is presented. So the goal was to see how to use the of electricity grid mix with different share of renewables and non-renewables for fertilizer production affects the results. So as you can see, the charts show the results of the comparison of environmental profiles of the 3 different cases in each impact category and for European and extra-European regions. So the worst case scenario, the one with the 100% value is chosen as a reference. The other scenarios are reported with a consequent percentage. So overall, the results show that for all investigated regions, the case 2 in orange, that is that one with the integration of CO2 capture technology, reduces the greenhouse gas emissions of more than 30% when compared to conventional ammonia production, the case 1 in blue. So these results depend on the degrees of direct CO2 emissions from the ammonia process, thanks to the CO2 capture unit. Specifically for the climate change category, we can see the highest environmental benefits in the Norway case, where a reduction of the impact up to 70% is achieved. In UK, the impact decreased by 53%. Can you move next slide? Okay. In US, the impact decreased by 40% in US, and in Saudi Arabia by 33%. The rest of environmental impact, no, can you come back to, okay. Okay, the rest of impact categories show a different trend. As you can see in the figure, case 2 the one with the CO2 capture performs slightly worse compared with the base case, especially in water depletion category. And this result is due to the additional plant consumption to capture and sequestrate CO2. So the case 3 in gray, the one with the ammonia produced from natural gas and water electrolysis, shows the highest overall environmental impact compared to the case 1 and case 2, due to the highest electricity consumption for the electrolysis process. The only exception is for the Norway case, where the case 3 has the lowest impact on 7 out of 16 categories. Okay, so in order to better understand the relative magnitude for each indicator and focus only on more relevant categories for the study, the LCA results have been normalized and weighted, dividing the characterized values by reference value. So in this study, the impact categories that cumulatively contributed to at least 80% of the total impact were climate change, photochemical ozone formation, acidification, water depletion, and mineral and fossil depletion. So since the greenhouse gas emissions, and in particular CO2, play an important role, here we present a special focus only on climate change indicator, expresses as a kilogram. So as you can see in the tables, the Norway case represent the most sustainable option for fertilizer synthesis if compared with the other cases, thanks to the highest share of renewable in Norway electricity mix, higher than 90%. Conversely, the Saudi Arabia represent the less sustainable option, since the share of renewables in the electricity mix is lower, only 1%. So I give the floor to Guido for the conclusion of the study.
Okay, thank you, Fabiana. The main conclusion of the study, as basically already indicated by Fabiana, are summarized in this slide. The results show that for all the regions, the CCS technology, that is the case 2 of our study, in the ammonia synthesis route, has a significant influence, reducing the greenhouse gas emission of more than 30%. The highest environmental benefit was gained in Norway, where there is an impact reduction up to 70%. The UK, US, and Saudi Arabia, as indicated, the impact decreased by 53% or less. But the rest of the environmental indicators do not follow the same trend, and this is the fertilizer production with the CCS technology, as we saw, performs slightly worse compared with conventional case due to additional plant consumption to capture and sequestrate the CO2. In the case of hydrogen produced from hybrid natural gas and the water electrolysis, that is the case 3 of the study, unless the electricity is obtained from non-fossil fuels, so renewable energy, this of course results in the highest overall environmental impact. Therefore, among the investigated regions, Norway might be the most sustainable option for urea and UAN fertilizers because of the significant environmental saving compared to the other cases. This is explained by the fact that the share of renewables in Norway electricity mix is higher than 90%. On the other hand, on the rest of the analyzed region, the share of renewables is sensibly lower. That goes from approximately 25% in UK, 17% in US, and only 1% on Saudi Arabia. And just to conclude, I think the study suggested that by transitioning to renewable electricity source for power generation and implementing a more sustainable production alternative instead of the SMR, conventional SMR, the overall environmental burden can be substantially reduced. There is, of course, room for probably for other study or to utilize the carbon captured for other scope like EOR, polymers, methanol, and therefore reducing the overall greenhouse gas emission. And of course, every alternative for CO2 utilization can be evaluated in terms of life cycle perspective. This is our last slide, and thank you for your attention.
Thank you very much, Guido. Thank you, Fabiana, for a very insightful and a very great presentation. I will encourage the audience to find the dashboard at the top right corner of your webinar platform and try to post as many questions as you would like to ask, and we will endeavor to answer these questions. Let me start by posing a few questions to the panel. With regards to the process of fertilizer production in Norway, you rightly mentioned that it generates way over 90% of its electricity from renewable energy. Why did you consider hybrid instead of 100% renewable?
Well, there are a couple of issues there. We in this study that has been carried out a few years ago, we tried to consider an electrolysis plant that at that time was operating. I mean, was a real electrolysis plant. So we tried to focus on something that was a real production plant, so not extremely big. The second point is that in order to produce urea, we need the CO2 because it's a feedstock for the urea synthesis, and therefore the CO2, unless you capture the CO2 from air, but we are talking about completely different technologies, you need to produce CO2 the carbon contained in the natural gas. So a certain amount of natural gas in this exercise was mandatory. Otherwise, we would not have any urea.
Okay, very well. Thank you very much, Guido, for that response. Another question I would like to pose to the panel is with regards to the CO2 capture efficiency. You obviously tagged the capture efficiency at 90%. Did you have any rationale behind that and not much higher that is about 97, 98 or 99% instead, because context of this study is deep decarbonization. So I think a number of audience are trying to figure out why it was capped at 90%.
Well, again, the one answer to that is that the study, repeat, was carried out a few years ago, and at that time 90% was a target, common target for carbon capture. If done today, we would probably go at least at 95%. That is considered today, I would say, a standard standard removal efficiency. So it's just the main reason is just because a few years ago 90% was a good target.
Very well, thank you very much for that answer. Another question I would like to put forward to the panel is, why normally best case the urea production is not maximized by capturing extra CO2 from a portion of the flue gas? Is there a cost efficiency reason here?
Well, we try to maintain the same product mix in all cases, just for easy of comparison. On the base case, since we follow the route from the ammonia to UAN via nitric acid. This is an example, but of course we choose this to explore this way. We need some ammonia for the nitric acid production and go to the UAN production. So in order to, we have chosen to convert to urea only based on the amount of CO2 that we can capture from the syngas. Of course, we would have converted 100% of ammonia by capturing the CO2 from the flue gas, no doubt. But in this case, we would have lost this this way to compare, to go up to the UAN, because no ammonia would be left for the nitric acid production. So this was a basic choice that we followed for all the three routes.
Thank you very much for answering.
This answer the question, but this is
we will encourage audience to get back to us in case if your answer has gone unanswered, so that we will be able to get back to you. Another very interesting question I would like to put forward to the panel is, CO2 is released after fertilizer application, and how does this reflect the concept of deep decarbonization?
So can you rephrase the question, please?
If fertilizer is being applied for food production, it is associated with release of CO2. So inevitably, some people, part of the audience, are trying to have an understanding. If the CO2 is captured, will that mean that some of the CO2 will be released after fertilizer has been applied for food production?
Yeah. Well, I think this is probably has been very slightly touched during the presentation. That is, it is true that when, for example, using urea as fertilizers, some of the CO2 is then released back to the atmosphere. This is something that it happens. But let's say that in this specific study wasn't the main scope. it is true. This is a fact, and we and Fabiana touch a little bit in one sentence this point, but for sake of the study, we haven't considered it. I don't know if Fabiana has something to add on this. Or...
Yeah, yes. For example, if you consider the life cycle of the fertilizer, and in particular, for example, in the agricultural sector, of course, you need to consider the CO2 emissions into the atmosphere in a life cycle perspective.
This one is also, this question is for the life cycle assessment team as well. The data for the life cycle inventory in the life cycle analysis is based on plants in Europe. Then how is this representative of other locations outside of Europe? The question is the data for the life cycle inventory that has been used in the life cycle analysis is based on plants in Europe. How is this representative of plants outside of Europe?
Not sure to understand the question. The technology is always the same in on the country, but the process and the database used have been chosen as country specific when available. For example, the electricity mix, or the data set have been made country specific, selecting regional electricity, gas, and water supply.
Thank you very much. At which point, another very interesting question, at which point is the electricity carbon intensity becomes low enough for case 3 to be better than case 1 and case 2? Climate change indicator only.
We don't have evaluated this aspect. We have the two extreme, the Saudi Arabia mix that is essentially all fossil, and the other extreme is the Norway electricity mix that is essentially all renewable. But we didn't have evaluated what is the trade-off to make one technology is better than the other.
Okay, very well. Before I continue, there are a number of questions asking how this study will be accessed. This study is free to access at the IEAGHG website for member countries, as well as corporate membership as well. I think a question being posed is that, would you want your PowerPoint presentation to be made public as well? Will you want your presentation to be made public? In any case, I think let me try to inform the audience that a record of this webinar will be accessible on the IEAGHG website and on our YouTube channels within the next coming days. So you should be able to get the contents. Thank you. Another question I would like to pose to you is, why did you include CCS for power generation in the United States and Saudi Arabia? This is a question from an audience.
Well, yes, this is well, this was part of the basis of design that were agreed to just to have a comparison on the same basis, in order to have in all four regions the same approach, even if some choice might be apparently not the most obvious, but the main focus was to have same approach on four very different regions, and this also I think is reflected also on the LCA results. This was just to have a common base for all regions considered.
Thank you for your answer, for your response, Guido. I think we will have one or two more questions before we round up. What techno have you used or simulated for SMR, CO2 flue gas, and syngas captures? What were the energy needs to do that?
You mean what technologies?
What techno? I would imagine the person asking the question means technology, but what techno have you used or simulated for the SMR, CO2 flue gas, and syngas captures? What were the energy needs for that?
Well, we for this study we haven't referred to a specific technology for all the process included, but we have taken from in-house data, let's say parameters that might be considered valid for whatever is the technology that we select. So there is no defined SMR technology or a defined carbon capture technology. In the broad terms, we can say that the carbon capture is being considered as an amine washing system for CCS. For steam reforming, of course, as wood, we have in-house the technology. So we have basically taken data from our in-house technologies, but at the end, this doesn't really make a big difference in terms of overall results of
Very well, thank you very much, Guido, for that question. I think we've run out of time. I would like to seize this opportunity to thank the speakers, Guido, Fabiana, Nicolas, Andrea, for all coming on board. Thank you also to the audience for giving us the opportunity to present the findings of this study to you. I hope that you found this webinar valuable, informative, and resourceful. So very well, thank you all. It's my pleasure to bring this webinar to a close. Thank you very much.
Thank you.
Thank you.
Thank you as well. Thank you all.